Should we wait, or is everyone here? It looks like, yeah. Okay. So just a quick recap of what we did last class. We looked at fundamentals of magnetic materials, right? We know what is the origin of magnetic field or magnetization in a material, or why materials are magnetic, right? And we see that there is only 3 elements in the periodic table that are magnetic elements, but compounds can be many, right? You can make lots of combinations of different materials. You can actually take some materials that are non-magnetic and make a compound that results in a magnetic material. So as long the criteria is you have to have unpaired spin, right? So as long as you can have unpaired spin, you get net magnetization. So that's the criteria. And you looked at different magnetic materials, ferromagnetic materials that has the highest relative permeability or susceptibility, which is equivalent to having high conductivity, right? So these are the materials that will give you high torque or high heating or high whatever it is. Sometimes change in resistance, sometimes change in polarization of the light, whatever it is, right? So these materials have because they have high B, so they will have higher effect on other properties. Okay, so today I think it's better if I just go all the way. Okay, so we wanted to look at some applications, right? We looked at what happened to the video of the car. Huh, interesting. I deleted it. Okay, anyway, so we looked at different, now this class is about applications, how magnetic materials are used in day-to-day applications. And we saw electric car, how it uses permanent magnet motor or hybrid induction and permanent magnet motor. And you can see here how permanent magnet motors are more compact than the induction motors. Induction motors don't have permanent magnets, but still induction motors still use ferromagnetic materials because they need high induction, meaning they need high B. Okay, they still use, but they use soft magnetic materials based on iron, cobalt, nickel. Whereas permanent magnets use the rare earths, neodymium, iron, boron, right? So our samarium cobalt is another permanent magnet material. I think I'll slightly close this. I think they're doing some work. So those are some of the applications in motors. But let's look at, this is normally I teach it in mechatronics. So this is basic principle how motors work by Faraday's law of induction. It needs this is a permanent magnet motor. It's not an induction motor. Here you have permanent magnets, and here there is a winding coil, right? It's usually copper winding, and when you pass current along this coil and in a magnetic field, so by Faraday's law of induction, FIB, take right hand, FIB. So you align your B in the direction, and current is going this way in the first cycle. So if the current goes that way and the field is this way, the force will be downward. So it will rotate counterclockwise. Okay, just use your, if I do, I have to do some acrobatics here. FIB, right? B is here, I has to go this way. So you see my thumb, it's downward, right? So that's the downward force on this arm. But the current comes back here, so it will experience upward, downward, upward. So you get a torque, right? So that's the basic principle of motor operation. And it's, again, high school physics. So that if you have AC, then you have some advantage there. If you have DC, you have to have different commutator. It's also your basic electrical, probably in first year you have studied in engineering. So that's how the motors work. They need a lot of permanent magnet for permanent magnet motors. If it's an induction motor, this permanent magnet is replaced by, what do you think it is replaced by? So you need a magnetic field, right, to get this rotating. So if you don't have permanent magnet in induction motor, what do you have? It's an electromagnet, right? You have another coil winding, so that it generates magnetic field, right? So you generate magnetic field by additional current instead of a permanent magnet. So obviously, you're sending more current instead of a permanent magnet, so the induction motors are less efficient because you need additional power source, right? Whereas if it's permanent magnet, you don't need additional current to get the torque. So that's why permanent magnets are more efficient. Permanent magnet motors are more efficient. And look at, if you take a DC permanent magnet motor, look at the linearity of current versus torque. It's so straight line, that two passing from origin. That means it's easy to control, easy to predict the torque. Just you want certain torque, give an equivalent current, you get certain amount of, it's very predictable. So that means this linearity, actuators or sensors, is very important. Okay, which means you can exactly get the amount of torque you want for a given amount of current, right? So you can change the current to get the torque you want by a simple expression. That is DC permanent magnet motor. For induction motor, the current torque relationship is not so simple. Okay, you need to know this relationship. It's not Y equals mx plus c. This is, it has a saturation as well. So it's a complex expression. As long as you know the expression, you can determine what is your torque for a given current. But it's not a easy. It's not linear. Okay, but the advantage is it can give you constant torque for a certain amount of speed, which is one advantage of induction motors. That's why at high speeds they are better, because you can keep the torque constant. So anyway, too much about motors. That's their one application. And now you come to more sophisticated applications. Motors are in fans, anything you, including your phones. Vibration you get is from a tiny motor with a cam shaft. It just does that. You can get vibrations, right? There are other ways also you can get vibrations, but I think having a small motor with a cam is easier. But for sophisticated applications such as robotics, you need to know it has to be much more precise than just saying, okay, I'll give you this current, give me this torque. It has to be much more sophisticated than that. So which means you have to have high resolution, meaning any small amount of current should give you a small amount of torque. So stepper motors are used that for that purpose. And here is a small video of a stepper motor.
Stepper motor is a brushless DC motor that.
Why is it not?
It got disconnected. So for now, we'll go with the Day session.
Okay, yeah, yeah, that's good.
It rotates in steps. This is very useful because it can be
Can you
precisely
hear?
positioned without any feedback sensor, which represents an open loop controller. The stepper motor consists of a rotor that is generally a permanent magnet, and it is surrounded by the windings of the stator. As we activate the windings step by step in a particular order and let current flow through them, they will magnetize the stator and make electron.
So in stepper motor, the permanent magnet rotates and the winding is current is from the stator. Whereas in DC permanent magnet motors, the magnetic field is coming from stator and the rotor is the coil, right? It's the other way around in stepper motor.
Magnetic poles, respectively, that will cause propulsion to the motor. So that's the basic working principle of a stepper motor. There are several different ways of driving the stepper motor. The first one is the wave drive or single coil excitation. In this mode, we activate just one coil at a time, which means that for this example of motor with 4 coils, the rotor will make full cycle in 4 steps. Next is the full step drive mode, which provides much higher torque output because we always have 2 active coils at a given time. However, this doesn't improve the resolution of the stepper, and again, the rotor will make a full cycle in 4 steps. For increasing the resolution of the stepper, we use the half-step drive mode. This mode is actually a combination of the previous 2 modes. Here we have one active coil followed by 2 active coils, and then again one active coil followed by 2 active coils, and so on. So with this mode, we get double the resolution with the same construction. Now the rotor will make full cycle in 8 steps. However, the most common method of controlling stepper motors nowadays is the microstepping. In this mode, we provide variable controlled current to the coils in a form of sine wave. This will provide smooth motion of the rotor, decrease the stress of the parts, and increase the accuracy of the stepper motor. Another way of increasing the resolution of the stepper motor is by increasing the numbers of the poles of the rotor or the numbers of the poles of the stator. By construction, there are 3 different types of stepper motors: permanent magnet stepper, variable reluctance stepper, and hybrid synchronized stepper motor. The permanent magnet stepper has a permanent magnet rotor, which is driven by the stator's windings. They create opposite polarity poles compared to the poles of the rotor, which propels the rotor. The next type, the variable reluctance stepper motor, uses a non-magnetized soft iron rotor. The rotor have teeth that are offset from the stator, and as we activate the windings in a particular order, the rotor moves respectively so that it has minimum gap between the stator and the teeth of the rotor. The hybrid synchronous motor is combination of the previous 2 steppers. It has permanent magnet tooth rotor and also a tooth stator. The rotor has 2 sections which are opposite in polarity, and their teeth are offset as shown here. This is the front view of a commonly used hybrid stepper motor, which has 8 poles on the stator that are activated by 2 windings, A and B. So if we activate the winding A, we will magnetize 4 poles, which 2 of them will have south polarity and here of them north polarity. We can see that in such a way the rotors.
So I think you got the idea. So these are the stepper motors which need both soft ferromagnetic material as well as hard ferromagnetic materials in order to um, get high resolution in a motor. So just recently, oh, this has come here. This is weird. What happened here? I know. So this is the proposal defense of a PhD student recently from University of Pittsburgh that I was in the committee. So this is, I thought, a nice uh, image that he presented. So these are all transformers, okay? So when electricity is generated by hydroelectric or coal power plants or nuclear power plants, whatever it is, they need to be supplied, and you use transformers to step up the voltage to really high voltage. We are talking in terms of megavolts or hundreds of kilovolts. You do that so that it has less resistance and you can transfer the electricity with little loss. Okay, so you step up. To step up, you need transformers, and for transformers, um, is it? So the work is going on there with the. So I think I'll have to just in in. No, no. What I meant is the work outside was bothering me, but that's okay. I think we will manage. Okay. So so the transformers are nothing but electrical steels. You take the regular steel, add some silicon, and you get what is called as silicon steel or electrical steel. So these steels also, you remember the soft ferromagnet and the hard ferromagnet. These are soft ferromagnets. They don't have any coercivity. Well, they have very little. When you see them, the area is very little, so there is no heat loss, because when they transfer the energy, the electricity, it's a AC signal, right? It goes from peak value to 0 to negative, and again it does 50 times. It's 50 hertz signal, right? 50 times in a second. So that means you cycle through the magnetization curve 50 times with that material, with transformer materials. So that means it should not have any coercivity. Then it won't get heated up. If it has any coercivity, it gets heated up. Okay? And usually the small coercivity you find in those electrical steels results in large heat. That's why these transformers are kept in oil bath. Okay? And most of the time you hear transformer blowout, it's because of overheating. Okay? So, and also you hear this humming sound, right? Has anybody experienced near transformer, you hear this humming sound, right? That's, does anyone know why do you get humming sound? No, even at low voltage you can get, doesn't matter, high voltage or low voltage. Humming sound is because of another property called magnetostriction. So when you apply magnetic field, a lot of the ferromagnetic materials change their dimension. Very small in terms of ppm we're talking about, say 10 ppm, and that small change in dimension creates some sort of vibration, right? And that vibration is nothing but a sound, and that's why you hear that humming sound due to magnetostriction. So you have to reduce magnetostriction, you have to reduce coercivity, and you have to have high saturation so that you can work with high voltages. So there is a lot of magnetic materials in power transmission. So starting with transformer, you need, of course, when it goes to wind turbines, you need permanent magnets to rotate when the wind is rotated, the voltage is generated because there is a magnetic field applied by a permanent magnet. And also in transportation, uh, if you have the bullet train, which works on maglev, that is, there are magnetic poles in the rails that allow the train to go fast. That's another application. So anywhere you take, even in electric cars, you have permanent magnets. So these are inductors and transformers. These two need soft magnetic materials, whereas generators and motors need permanent magnets. Okay, so for permanent magnets, you need very high coercivity. For soft magnets, that is for inductors and transformers, you need very low coercivity. Okay, so this is how. Uh, okay, so this is a big industry. Earlier, before 20, 2000 or before 2000, whole magnetics research was all about this. But then came the magnetic storage. Okay, so data storage. We'll talk about magnetic data storage soon. So any questions until here? How the magnetic materials are used in motors, generators, transformers, or inductors. We did not talk much about inductors, but that's okay, because inductor needs concept of induction, which is a big thing in circuits. Okay, whereas transformers, you understand, right? Voltage has to go up when needs to be transmitted. So you need electrical steel here. These are laminates of electrical steel. You can't just have a big core of electrical steel. They have to make thin slices of electric steel so that there is no eddy currents. Okay, so that's all soft magnetic material. And the hard magnetic material is in motors and generators. Any questions so far? Okay, let's move on then. So now let's come to another very important application of magnetic materials, which is data storage. What are different modes of data storage? How is data stored? So all your videos, your Instagram posts, Facebook posts, YouTube videos, name any film in the world, any documentary, any presentation that's there in YouTube, right? How do you think such a large data is stored? Yeah, that's through data servers, but how? What data? What is data server? Yeah, but how is it stored? I mean, you are an engineer, right? We want to know how we want to make it happen. So, yeah, data servers. What are they? Hard disks, SSD, your USB stick. is nothing but an SSD, right? Now, USB sticks, what capacity do you get nowadays? Sorry? 2 TB, yeah, I mean, depends. I think 2 TB is what I have seen as well. So maybe give one more year, there'll be 4 TB or USB stick, right? So when I was doing undergrad, I was, of course, mechanical engineering was my branch, and I was also doing computer course from Aptech. There was something called Aptech Academy for learning computers. And I used to learn programming languages outside of my syllabus, and we used to carry these floppy disks. Those are 5.5 inches this big, floppy disks. Do you know what was the memory capacity of those disks? Yeah, how many KBs? 500 KB. So 1 megabyte, you can understand, right? 1,000 megabytes make a gigabyte, and 1,000 gigabytes make a terabyte. And 500 to 600 KB was the hard capacity of those hard disks, those floppy disks. And then came the 3.5 disks, smaller ones. And the capacity of that was 1.4 to 1.5 megabytes. And we were so excited that, oh, it's double, almost double the memory. And we used to carry it around in our cargo pants. So yeah, USB sticks did not exist. And these floppy disks, and then came CD, compact disks. Compact disks, how do you think data is stored in compact disks? Nobody said about compact disks or DVDs. How do you think data is stored in DVDs or CDs? Okay, we can come to the floppy disks and hard disks. But how do you think the information is stored in any media? Doesn't matter, CD, hard disk, or even in RAM. How is the data transmitted? So if I take a photo or audio, how do you send it to the microprocessor or operate on it? How do you store it or signal process it? Yeah, so you can digitize it, right? You take the analog signal and break it down into certain digits, and then convert them into 0 and 1. So you have only two options of signal, 0 and 1. So when you transmit that 0 and 1, so if you have a small information, when you break into zeros and ones, it becomes a lengthy information, a lengthy signal, because it's ones and zeros only, right? So, but it's easy. That's how we can represent in current and no current. That's how the transistors work. Transistors either are turned on or off, and that's what is the information, ones and zeros. So, and you also store in ones and zeros, whether it's hard disk, floppy disk, SSD, or even compact disk. In compact disk, it's optical, meaning you make a permanent change on the disk, which is you make a track dark or reflective, and you can reverse it in writable CDs or writable DVDs. So in CDs, you make it dark and light, right? What do you think happens in floppy disks or hard disks? So, and when it is very small track, you put lots of ones and zeros, and that's your information, and that you decode it again. The way you encoded it, you decode it, and it becomes your photo, your music, your video, or your pure data, right? So how do you do that so in CD, it's you burn tracks, light and dark, that becomes ones and zeros. What do you What do you think in hard disk? What do you think happens in hard disk? Answer is here. You magnetize in one direction, that's your 1. You magnetize in another direction, that's your 0. Okay, so that means you magnetize in 2 directions, that becomes your 1 and 0. Okay, so but then how do you magnetize, and what's the size of your magnetic bit? In CD disks, it's tracks, right? In tapes, there were also tapes. Have you seen an audio tape or a video tape? So those are also magnetic tapes. They're nothing but iron filament that is pasted on a polymer, and the right head goes and magnetizes zeros and ones in there, and then reads it back. Okay, the read head. There is right head, read head, and the tape. So there are 3 things in any data storage. One is the writer, the other one is the reader, and the other one is the media. Okay, so that's the same thing in hard disk as well. Hard disk or floppy or tape, you have the same thing. There is a reader, there is a writer, and there is a magnetic media. Okay, so the magnetic media should be able to, if you write if you magnetize one small area, it should retain that magnetization, right? Then you should be able to erase it and rewrite. Okay, that should be the property of media. That means the right head should be able to apply a large magnetic field to write it. Okay, the read head should be able to read whether that bit where it is reading is magnetized or not, right? So those are the 3 important things for data storage. And just imagine if you were not able to store data, right? So if you go to the data centers I was talking about in Virginia, in Richmond, in the first presentation when I gave an introduction about Richmond VCU, the data centers have racks and racks of hard disk drives. Okay, and all the data that you consume today, all the videos, all the audio and photos, it comes from those hard disks. Somewhere it is stored. Okay, and that is stored in the form of magnetic bits, or magnetization and no magnetization. So now let's, each of them, the media has to have certain property. It has to retain magnetization, and the right head should be able to apply large magnetic field, and the read head should be able to read any small magnetic field. So the sensitivity of the read head should be good. The right head should be powerful enough to write. The media should be robust enough to retain the information, right? That's what is needed for a magnetic data storage device. So hard disks are the ones that have the highest capacity. Floppy disks, because they're just magnetic paint on a polymer. Floppy disks are round, it's same as tape, but it's a round disk, and it's divided into sectors, slightly more sophisticated than the tapes. But hard disks are much more sophisticated because their media is a special material, and the media in a hard disk drive is very which means you can write each magnetic spin or a domain in a very small area. And nowadays the domain width is in terms of 30 to 40 nanometers. Okay, yeah, so So people, when they started using hard disk drives, the need for this data storage was not that demanding. Meaning, if you have a hard disk drive that has 512 megabytes, it was really big amount of memory. So people could write or make one domain. The hard disks are, their size have remained the same. Hard disk size won't change, because if you change the size of the hard disk, your computer will become big and everything else will change. So the hard disk size is about 5 inches. That's the same. So because the memory was small, you could write in a bigger domain. So each domain was about 100 to 300 nanometers. That's why you could just put them longitudinally like this. One direction is 0, the other direction is 1. But when you started to squeeze in more data, if you start to make these pins really small longitudinally, the reader will find it hard to read longitudinal domains so close by. So you have to magnetize the media perpendicularly. So each domain, this 50 nanometer or 30 nanometer, you can now magnetize up or down. Okay, here it is 100 to 300 nanometers. Here it is 30 to 50 nanometers. So you can squeeze in more data here. Okay, so here is usually, this is a write head, and usually write head, I have other better images. So this was the first hard drive by IBM. You see the size of that. And you know what's the capacity of that? 5 megabytes. So I heard the first hard disk in India was imported by IIT Madras. And apparently they had to break open their wall to bring it in. And that's 5 MB. And I think this is the next version. They have stacks and stacks of disks here to store about 5 or 10 MB. And the cost of that was $10,000 per megabyte. So that means this was $50,000. And $50,000 back then is now easily $500,000. So now you can get 4 or 8 terabytes. I don't know, in Indian rupees, it would be 7,000 rupees or 8,000 rupees. You can get 4 to 6 terabytes hard disk. Terabytes from 5 megabytes, you'll get 1,000 times increase. And this is how the hard disk looks like. Usually when I bring a hard disk, open hard disk and circulate, but it's in my lab in VCU. When I teach this class, I bring a floppy disk, hard disk, a opened motor, permanent magnet motor, a stepper motor, and circulate among students just to get a feel. But yeah, I could not put them in my luggage. So this is a same hard disk drive. This is the write head. And as I said, write head should be able to write with very high magnetic field. What does that mean? That means it should have very high saturation magnetization, right? And it should not have coercivity, because you will be writing so many times, it should not heat up. And what do you think is the read head? It has to read. What do you think it is made of? How does it read? What is it? What is a read head? It senses small magnetic field. Some magnetic sensor, but what is that sensor? but how will particles sense? But, and then, so the particles align, but then what happens? You can't see the alignment. How will you measure the alignment? So I think you are getting there, but so that's one way you can build a sensor, but this sensor is built on a phenomena called giant magnetoresistance. Okay, so this was discovered by two people by name Albert Fert and Peter Grunenberg, and they simultaneously discovered that phenomena wherein they were looking at resistance of materials, and when they put three magnetic thin films together, they saw that the resistance suddenly jumped up, although all three are conducting materials. Okay, so they realized that there is a quantum magnetic effect. When three magnetic layers are interacting, they don't allow the electrons to conduct through the three layers. And that was used, that's called giant magnetoresistance. So that can be used as a sensor. So that means whenever it senses a magnetic field, its resistance jumps up. So if its resistance jumps up, you are providing a voltage. If there is no magnetic field, you get a current because there is no resistance. But suddenly, if its resistance jumps up because it sees a magnetic field, then current either becomes very low or, so that's how you sense it. You sense any magnetic field or magnetic domains. Okay, so they both got Nobel Prize in 2008 for discovering giant magnetoresistance, and that changed or increased the storage density so rapidly, and hard disks became so cheap. Okay, so that is giant magnetoresistance, and I think this video will give you a nice overview of how the hard disk is built.
A home computer is a powerful tool, but it must store data reliably to work well. Otherwise, it's kind of pointless, isn't it? Let's look inside and see how it stores data. Look at that. It's marvelous. It's an ordinary hard drive, but its details, of course, are extraordinary. Now, I'm sure you know the essence of a hard drive. We store data on it in binary form, ones and zeros. Now, this ARM supports a head, which is an electromagnet that scans over the disk and either writes data by changing the magnetization of specific sections on the platter, or it just reads the data by measuring the magnetic polarization. Now, in principle, pretty simple, but in practice, a lot of hardcore engineering. The key focus lies in being sure that the head can precisely, error-free, read and write to the disk. The first order of business is to move it with great control. To position the ARM, engineers use a voice coil actuator. The base of the ARM sits between two powerful magnets. They're so strong, they're actually kind of hard to pull apart. There. The ARM moves because of a Lorentz force. Pass a current through a wire that's in a magnetic field, and the wire experiences a force. Reverse the current, and the force also reverses. As current flows in one direction in the coil, the force created by the permanent magnet makes the ARM move this way. Reverse the current and it moves back. The force on the ARM is directly proportional to the current through the coil, which allows the ARM's position to be finely tuned. Unlike a mechanical system of linkages, there is minimal wear and it isn't sensitive to temperature. At the end of the ARM lies the most critical component, the head. At its simplest, it's a piece of ferromagnetic material wrapped with wire. As it passes over the magnetized sections of the platter, it measures changes in the direction of the magnetic poles. We call Faraday's law. A change in magnetization produces a voltage in a nearby coil. So as the head passes a section where the polarity has changed, it records a voltage spike. The spikes, both negative and positive, represent a 1, and when there is no voltage spike, corresponds to a 0. The head gets astonishingly close to the disk surface, 100 nanometers in older drives, but today under 10 nanometers in the newest ones. As the head gets closer to the disk, its magnetic field covers less area, allowing for more sectors of information to be packed onto the disk surface. To keep that critical height, engineers use an ingenious method. They float the head over the disk. You see, as the disk spins, it forms a boundary layer of air that gets dragged past the stationary head at 80 miles per hour at the outer edge. The head rides on a slider aerodynamically designed to float above the platter, and the genius of this air-bearing technology is its self-induced adjustment. If any disturbance causes the slider to rise too high, it floats back to where it should be. Now, because the head is so close to the disk surface, any stray particles could damage the disk, resulting in data loss. So engineers place this recirculating filter in the airflow. It removes small particles scraped off the platter. To keep the head flying at the right height, the platter is made incredibly smooth. Typically, this platter is so smooth that it has a surface roughness of about 1 nanometer. To give you an idea of how smooth that is, let's imagine that this section is enlarged until it's as long as a football field, American or international. The average bump on the surface would be about 3/100ths of an inch. The key element of the platter is the magnetic layer, which is cobalt with perhaps platinum and nickel mixed in. Now, this mixture of metals has high corrosivity, which means that it will maintain that magnetization and thus data until it's exposed to another powerful magnetic field. One last thing that I find enormously clever, using a bit of math to squeeze up to 40% more information on the disk. Consider this sequence of magnetic poles on the disk surface, 0, 1, 0, 1, 1, 1. A scan by the head would reveal these distinct voltage spikes, both positive or negative for the ones. We would be easily able to distinguish it from, say, this similar sequence. If we compare them, they clearly differ. Engineers, though, always work to get more and more data onto a hard drive. One way to do this is to shrink the magnetic domains, but look what happens to the voltage spikes when we do this. For each sequence, the spikes of the ones now overlap and superimpose, giving fuzzy signals. In fact, the two sequences now look very similar. Using a technique called partial response maximum likelihood, engineers have developed sophisticated codes that can take a murky signal like this, generate the possible sequences that could make it up, and then choose the most probable. As with any successful technology, these hard drives remain unnoticed in our daily lives unless something goes wrong. I'm Bill Hammack, the Engineer Guy.
So, yeah, I mean, to get there, it did not come there by magic. People started with magnetic tape, and eventually we are here at hard disk drive. And it's people like you and me who, are interested in doing some research in material science. This is all material science. How you increase the coercivity of the platter so that it can retain the information. How you increase the saturation magnetization of the core that writes. How you increase the sensitivity of the magnetoresistance sensor. That's another material science problem as well. So this is done by people who are interested in working at fundamental level or doing research. So it's a research that is accumulated over 80 to 90 years has resulted in hard disk drives that now allow us to store terabytes and terabytes of data, which means we can access to any video we want, we can store any video we want. So that is done by all this research, okay? Coming back to the platter, the disk. So the disk, you saw it's a combination of several layers. And of course, on the top is a layer that is a kind of polymer that allows, if the head doesn't touch the platter, but if by any chance touches, it just slips, it doesn't damage the disk. So here it is evaporated glass, but it can be a polymer that has high lubrication property. And the magnetic layer is only 50 nanometer. This could be cobalt ferrite with platinum or cobalt platinum, or there several materials have been used by different hard disk drive companies. Do you know any hard disk drive company? Like sorry? Western Digital, WD, and Seagate. Yeah. So you guys are familiar. And they had really large research centers where lots of uh, research scientists worked, and they were mainly material scientists. And for recording the signal and storing it or converting it, those were electrical engineers. And then converting from analog to digital, these are computer scientists. Okay, but bulk of the work was done by material scientists and mechanical engineers. Many mechanical engineers as well, for building the hard disk drive so that it doesn't degrade over the time, or small dust or little temperature increase won't damage it. Okay, so this is, and the substrate, it's not plastic, it's silicon, but if it is plastic, you won't notice it because there are so many metallic layers. Okay, so that is several layers, and these are thin films, meaning 50 to 100 nanometer coatings. That means you have to have very sophisticated machine that can deposit nanometer layer of material. Okay, so when you look at the hard disk drive, the magnetic layer, cobalt, iron cobalt, or cobalt platinum, or gadolinium terbium. So this is how the domains look like. And these are also, so here is one place where you can assign one grain to one domain. Okay, so each of them can be considered as a domain, but they are also grains. So you basically, these are polycrystalline samples with different grains, and each grain can be a domain. Okay, not can be a domain, is a domain. Okay, so you can magnetize each domain or group of domains, these domains up and these domains down. So when the sensor reads, different tracks have different information. Okay, so, and the tapes, of course, this is 18 nanometer. Each domain is few nanometers, whereas the tapes have much bigger, these are not even grains, these are needle structures. So those have, each needle structure has multiple grains. So those are slightly bigger, and you again magnetize certain group of needles to record either 1 or 0. Okay, so similarly, other media, I think this is tape as well. So tapes, depending on how you deposit, either screen print it or spray it, you get different microstructure. Okay, so now the question is, how much, I mean, now we can store 8 terabytes in a 5-inch disk, right? Why only 8 terabyte? Why can't we store 100 terabytes? What's limiting us? So this is our media, right? This is the disk. Why can't we store 100 terabytes? Why only 8 terabytes? Yeah, grain size. So that means you can make the grain smaller and smaller. Yes, you can make grains even sub-nanometer, but can you read it? Can the sensor be that sensitive? Okay, even if the sensors are that sensitive, can you move your sensor nanometer by nanometer, right? You have to move your sensor, right? If you have to read different ones and zeros, it has to go from one grain to another grain to read, right? So can you control so precisely your sensor to move 1 nanometer by 1 nanometer, right? So it's an engineering challenge. So sensor is one thing. Controlling the sensor motion is another thing. Yeah.
The center shape of the white thing is an oxidized one. So when they are not reading, only the grain size reads. So is it that only the darker surface is where the data is stored?
It doesn't matter. I mean, you can choose whether you want to have darker size as +1, -1. You magnetize or non-magnetize. You magnetize in one direction or other direction. But the concept here is each grain you can magnetize in one or the other direction.
Which means the white part is, the lighter regions are not the storage parts.
No, it doesn't. The color doesn't mean anything unless darker regions. Okay, so in this media, the grains, there are different types of grains. One is cobalt chromium separated by oxide layers, and oxide layers cannot be magnetized. So this is an older disk, although it is perpendicular media, because nowadays each bit is read in a grain of 30 nanometer size. So you don't have option to make oxide grains there. You have all the grains that are magnetic in nature, and each magnetic grain is either magnetized in one direction, up direction, or down direction. Okay? Yeah. So just like here, right, these tapes, these have lots of gaps, and this is the only magnetic material. Likewise, they are separated by oxide layers. I did not notice that, but because, yeah, I have looked at other latest ones, and I've studied latest ones. Yeah, so now imagine that you have each of these disks that can be magnetized in specific direction, and you can control. So the limiting factor is one, the sensor sensitivity. The other one is reading at a very small range. And the other one is the media itself. You can store with 30 nanometers is okay, but when you go closer, you can lose the information just because of rise in temperature. Because when you start making the grain smaller, that means you need less and less field to demagnetize it. When you have a larger grains, you need larger field to. So in simple terms, the energy needed to demagnetize a smaller grain is much smaller than the energy you need. This is the anisotropy energy, Ku. That depends on the grain size. Okay, so that's why. So Ku multiplied by the volume of the grain divided by kBt. If your temperature goes up by a small distance, a small amount, you can demagnetize the grain. So this product has to be always above 70. Okay, so that means your volume has to be high, anisotropy energy has to be high, and this we can't change much because that depends on the material intrinsic property. The volume, larger the volume, more stable is the media. So if you start making the grain smaller and smaller, you have higher chances of losing the data. Okay, that's what it means. So you can't squeeze in 100 terabytes in a 5-inch disk, because if you want to do that, your volume of the grain should be very small, which means you will have higher probability of losing the data. Okay? So, and now the other option is to make the anisotropic energy really high. But if you make the anisotropic energy very high, you have to have a write head that is really, really powerful. We don't have very powerful write heads. The highest saturation magnetization has a limit. The best one is iron cobalt write heads, and those are 2.4 Tesla saturation magnetization. And if you increase this, we don't have other materials to increase. So what people are now doing is you increase this anyway, but when you're writing, you use the same head which you have reached the limit, but while writing, heat it so that you need our regular write heads that are there with the materials available now can write it, because at higher temperature, the top the anisotropic energy becomes low, so you can use smaller field to write it. Okay, so if you increase this, then you have to bring another mechanism. These are called heat-assisted magnetic recording. Either this could be laser, or people also have used microwave, but the laser one became more popular. It's commercially more feasible. They exist in the market nowadays. Heat-assisted magnetic recording. Okay, so we have already reached the saturation magnetization. That means write heads can't improve anymore. If you can make a write head that can have saturation magnetization about 2.4 Tesla, you can be an instantaneous millionaire. So a lot of people have worked on it. So that is the frontier now. Okay, and then people are exploring 3D instead of 2D. So in 3D, the problem becomes, how do you read it? So in here, reading is you just move, but here you have to move not only laterally, but also vertically, right? So there are certain ideas how you can move the data. Instead of moving the read head, you make the magnetization move. Okay, so that is another way of, but people think this is just a pie in the sky idea, it will never work. Okay, so and the other proposed one is you can make the bits, each individual bits separated, use lithography, as opposed to, you saw the clusters of grains, right? Instead of clusters of grain, you write each grain separately in a certain pattern, which means you have to use nanolithography, which is done for processors and microchips. So you use that one, but then the process becomes very expensive. This is another idea which can increase the memory density. So how are we doing? We have another 20 minutes. So this is PMR, that is perpendicular magnetic recording. What you saw in the video is parallel, right? It's not perpendicular, lateral, right? So that is an old video as well. Now you have perpendicular media. That increased storage density quite a bit. And then came PMR plus. I don't know what that did, but after PMR is the hammer, heat-assisted magnetic recording. That increased the density quite significantly high, which is, this is, so we used to, terabyte per inch square was the, when I was, this one 1 terabyte per inch square, reaching this was a big milestone. This is when I was doing PhD No, this, I thought they reached this much earlier. But anyway, so 1 terabyte per inch square was a big milestone. If you could reach 1 terabyte per inch square, that was unfathomable. But now you can get almost close to 10 terabytes. Okay, so this is Hammer. We are here right now. Somewhere, oh, we are already here. HDMR is heated dot magnetic recording. So basically, they are improving the media and using the heat laser. Okay, so that took a lot of research, because when you do the laser heating and cooling has to be so fast. You know how fast the disk drive rotates? 7,200 revolutions per minute. Per minute, 7,200 times. So that's a high speed. And yeah, and when it is moving like that, it's reading so much data. That means your laser has to be heating and cooling so fast. And that is one of the limiting factor there. Okay, so that's about magnetic data storage. That is one of the biggest achievement of, apart from, of course, motors, transformers, data storage is one of the big milestone of magnetic materials or magnetics in general. Yeah. Any questions about this, about data storage? And now a lot of people don't use hard disk drives, right? What do you use? SSD, right? So you would imagine that the market has gone down, but not really. What you have done is you reduced your use of hard disk drives by moving all your data to data centers, and data centers have increased the use of hard disks. So although it has reduced a little, it has plateaued. The way they count is number of hard disks shipped per year has kind of saturated now, is saturating now, because there is no consumer grade, consumer level. It's not, people are not using hard disks, but the data centers are using. So it is plateaued because of SSDs. So SSDs, of course, they're smaller, faster, but SSDs for the same capacity, they're much more expensive, right? And what is the other difference? Why do you think then not all the hard disk, all the data centers are using SSD? What's the, apart from the size and speed, what is another major difference between hard disk drives and SSDs? Yeah, price is, SSDs are more expensive for the same capacity, but yeah, price is one thing, but they will become cheaper anyway. They'll start to become cheaper. I mean, it's just a matter of time. Reliability. So any small mechanical damage to an SSD, you will lose the data. But any damage to hard disk, you can retrieve the data. It's all there in the platter. Okay, and also the lifespan of SSD, the way it works is what is called as a floating gate. So it depends on how you push the charge in an insulator. Yeah, just like how we magnetize and demagnetize, there we are making a small layer conductive and non-conductive. The way we do that is by pushing the charges to one layer, and that becomes conductive, push the charge to the other layer, becomes non-conductive. And that is more sensitive than the hard disk platter when you magnetize and demagnetize. When you magnetize, so the cycles can be a, a lot of cycles you can have, magnetization and demagnetization, whereas the charge movement, after a certain number of cycles, they degrade. So that is another. One is the reliability, and the other one is the duration or the lifespan, number of cycles you can write. So that's another major difference. Okay, any questions so far? Now, these are the three, the transformers, motors, and the data storage are three major things of magnetic materials. Then there are many smaller things, okay? MRI, in medical imaging, in actuators, in stress detection, and so on and so forth. Those are also good. I mean, they're nice applications, but the market is not very big. They did not revolutionize the whole society. Like, imagine if we did not have the data storage which was enabled by magnetic storage, we would have not have access to information so much. So the other application is what is called as non-destructive evaluation. Okay, so I'll go over it, and then it'll take probably 5 minutes and then break off. Okay, so this is another technique wherein you can use magnetic materials or magnetic field to determine microcracks or nanocracks, or even sometimes residual stresses. So what happens when you take a magnetic field and put it on a ferromagnetic material? The flux lines go through, right? And flux lines like this and come and join. And if you keep another sensor here, magnetic sensor, which is a Hall sensor, you can read how much flux is going through. And you can, depending on there is primary coil and secondary coil. Primary coil, you supply the current and you know how much field it is generating, and the sensor should generate so much field. If there are any microcracks, the flux lines deviate. When the flux lines deviate, your sensor will show different amount of magnetic field. This is a sensor which is a secondary coil. Basically, the nice thing about generating magnetic field and sensing magnetic field in crude sense, okay, not the data recording, that's very sophisticated, but in here it's a crude sense. Look at this, is how he generates magnetic field. It's this big. You just take a iron core, wind some copper wires, and supply some current to that wire. Depending on the number of turns and the amount of current, you can determine what's the magnetic field coming out of this big yoke, right? Iron core yoke. So you generate a magnetic field. Now you place another winding coil just in between somewhere that senses the flux line. So as soon as the fields are formed, the coil here that is not connected to any current will have an induced electric field, because as soon as the flux come, a time varying magnetic field will induce a current in these coils. So that's called secondary coil. So secondary coil can be used for sensing magnetic field. So you always have a primary coil and a secondary coil. So primary coil generates the field, secondary coil reads the field. Okay, so it's not very complicated to do this. And so when secondary coil reads, and depending on what level of cracks and stresses you have in the material, the secondary coil will read different amount of magnetic field. And that is one way people go through these big pipelines that are used for either supplying petrol or gas or whatever it is, or water, to see if there is any micro cracks or any damage. But it's a manual process. Even aircraft wings earlier, which were made of some ferromagnetic material, now it's all composite and aluminum, some aluminum alloy. So you can't use, for this to work, your material structure has to be ferromagnetic material, right? If it's not ferromagnetic, it doesn't matter. The flux won't go through and it doesn't matter. So that is called NDT, non-destructive testing. And the other one is slightly more sophisticated, is where you can, it doesn't matter with the cracks or micro cracks or nano cracks, even if there is residual stress, you can sense it. This is much more sophisticated and complicated concept, wherein you know this curve, right? When you apply magnetic field, you get increase in B or M, right? Magnetization. But this magnetization goes like this and saturates. But if you zoom in your this curve, the magnetization increases not so smoothly like this. It's like it's a step behavior, step increase or a step function. Do you know why that is? So, yeah, we did not cover that, but I'm hoping somebody can guess. So when we increase the magnetic field, of course, in different axes, you have different permeability, different materials will have different level of increase in the magnetic field. But if you zoom that in, you find that's the same thing with the hysteresis curve as well. You zoom it in, you see these steps. Why do you think that is? Sorry? Voids? No, not really. If there is no voids in the material, even if it's a single crystal perfect sample, we'll still see those steps. Sorry? No, if it's a single crystal sample and same material, same single phase, then also you get these steps. So you have to think in terms of how the spins reorient. You remember this? Remember that? What's happening here? Domains are moving, right? They're realigning. So how do you think they will move? It's not smooth aligned. They will only move when they get enough energy. So it's like a quantized energy. So once you get enough energy to move this domain moves, right? So the domains keep moving, or each domain needs certain energy to move. And as soon as it moves, you get a jump in magnetization. So it has to, the magnetization increases when the domains align in the magnetic field, right? So that domain alignment or domain motion is a step function like that. And that domain motion, you can pin it depending on how many dislocations you have or point defects you have. So one of the way to increase coercivity is by pinning these domains. So introduce a dislocation or a point defect, the domains take more energy to move. Then you get larger steps. So when you pin the domains, you also get larger coercivity. Okay? So these step-like functions can lead to sudden increase in magnetization, right? And that sudden increase in magnetization can be read by secondary coils because that's a jump you see in magnetization. So it's a sudden increase in magnetization by step function. So that yeah, so that can be read by a secondary coil. Okay, and this is discovered by a guy called Barkhausen. So that's why these are named as Barkhausen emissions. So you see these burst of noise coming into your secondary coil when you are, so it looks like this, bursts of small signals in secondary coils, but they're very small. And so that means larger the jump, that means domains encountered lots of dislocations, right? Or lots of point effects, which means it can tell you dislocation density, which is nothing but a measure of residual stress, right? So you can correlate these jumps to the stress in the material. And it's not a straightforward correlation. So if you want to correlate that, this is the equation that correlates the Barkhausen jump. That jump results in a Barkhausen voltage called VB, okay, is given by the mu naught, the ND is the, this is the, oh my God, I forgot, demagnetization field. This is the demagnetization field, and this is M reversible. Again, reversible, this is irreversible. This is changing delta H, and this is the area. So it depends on all these parameters, and that can be correlated to residual stresses. So it's again very, so if you have a stress-free material, your jumps are smaller, but if you have a tensile stress, it's much bigger. A compressive stress will decrease the signal compared to stress-free material. Okay, so with that, I think I'll conclude the magnetics chapter. We'll look at another special kind of magnetic materials, which is my research, which is related to refrigeration and cooling. But this is magnetic materials, fundamentals of magnetic materials and its application. I teach it as a subject. So I taught it in 2 classes. Okay, so this is a whole subject by itself, magnetic materials. And of course, we solve problems, we calculate the saturation magnetization, we calculate the coercivity, and so on and so forth. So now think of 3D printing these materials, right? Because the transformers or the generators or motors, they need complex shapes, of course. Okay? So regular machining will either induce some residual stresses or is not possible in many cases. Remember that stepper motor, how complicated it was? Machining that with a magnetic material is really hard. That's why we need additive manufacturing. So in additive manufacturing, we can control, because it's layer by layer, we can control quite a lot of things, but also it's slow process. And getting the right density is also a challenge. Okay, so I think with that, we will, it's already 11:02. We'll break for coffee or tea. And then at 2 o'clock, I will talk about magnetic refrigeration, okay? A new area of research. It's what I did my PhD in. We'll talk about that, okay?
Sir, thank you for the
Thank
wonderful
you.
presentation.